So the first thing I'm going to do to determine the H-NMR signals in this molecule is to draw in the hydrogens. I'm just going to put them in as like lines because if I keep writing H's, it's going to get repetitive because we're going to go through a couple examples here. So these methyls are going to get just 3 lines for the 3 hydrogens on them. And these methylene groups, I'm going to have one sticking out and one going in the back. So one coming out at us, one going in the back, coming out at us and going in the back. So what is this methyl C? If we go this way, we're going to see a CH2 group, and if we keep going, another CH2 group and another CH2 group, and same thing with this methyl group. If we go this way, we're going to see CH2, CH2, CH2. So their environments are the same, so we're going to call them the same signal. I'm going to highlight that in the same color to show that they're equivalent environments. They're going to have the same chemical shift because they're experiencing the same things, if you will. Now, what about if we take a look at the methylene groups? So this CH2, if you go on one side, you're going to see a CH3, but you're going to go on the other side and you're going to see a CH2. So if one side we have a CH3, one side we have a CH2, is there anything else that's the same as that? This one. If we go on one side, we see a CH3, and on the other side, we're going to see a CH2. So we're going to call these two environments equivalent. So these two have the same signal. What about this one down here? It's a CH2 group as well, so why isn't it the same as these two pink signals? Well, the reason is because this CH2 is in between two CH2s. It's not, for example, this one is immediately next to a CH3, this one is immediately next to a CH3, but this one is only sandwiched between these two methylene groups, so it's going to have its own signal. It's unique, therefore that's the third signal. So for this molecule, we're going to have a total of 1, 2, 3 signals. So 3 H-NMR signals for this one. So let's take a look at this next example. Let's fill in the hydrogens. So we have 1, 2, 3, and we see over here there's 3 bonds to this carbon, so we're going to add 1 hydrogen. Same for this one, same for this, and go around. And we see that this carbon already has 4 bonds. Okay, so now we have our hydrogens labeled, and now we have to see which environments are the same. So for this one, this is like the only methyl sticking out off of the benzene ring, so it's going to have its own signal. There's nothing else like it in the molecule. These two are going to be considered the same signal because if you go up here, you see the same thing for either one. And if you go down this way, you're going to see the same thing for either one, no matter how far down you go. Okay, so these two are going to be the same signal. Why wouldn't these two be considered the same as the ones up there? Because here, where you can go up here and see a CH3, these ones, they don't. You would have to go past these and then go to the CH3. So these are going to be a different signal. This is going to be our second signal. And this is going to be very unique because it's on the opposite side of this CH3 and you would have to go up 3 to get to it. So it's going to be different than the rest. It's going to be its own unique signal as well. So for this molecule we have 1, 2, 3, 4 unique signals on our H-NMR spectrum. So previously we said that these were going to be, this signal was going to be different from these two hydrogen signal because these would have had to go up 2, 1, 2, you know, like to get to the CH3, whereas this one only had to go up like 1 step. But over here we see if you go up this way, you get to the CH3 just the same as if you go down that way. It's the same distance, so they're technically seeing the same things. So that's why these are all going to be considered one signal this time. They're all equivalent. And then these, of course, would be their own signal because they're both CH3 groups coming off of the benzene. Okay, let's label the hydrogens for this example. 1, 2, 3. 1, 2, 3. 1, 1, 1, 1. This is a methyl coming off of a benzene. This is a methyl coming off of a benzene. If we go this way, we see this hydrogen sticking off the benzene. If we go this way, we see this hydrogen sticking off the benzene. Therefore, they're equivalent, because if you go the opposite way, we see 1, 2, 3, and for this one, we also see 1, 2, 3, so they're the same. So these two methyls are going to be considered the same signal. This hydrogen here is a unique signal because it's the only hydrogen sandwiched between two CH3 groups. Similarly, this is going to be its own unique signal because it's the only hydrogen that's sandwiched between another H and another H, and then the CH3 groups. This hydrogen and this hydrogen are going to be the same because if we go this way, we see that same hydrogen, and if we go the other way, we see a methyl group and a methyl group. So they see the same things, they have the same environment. So we're going to say these are equivalent, but this one is not. Let's draw in our hydrogens for the next example. 1, 2, 3, 1, 2, 3, 1. So 1 coming out, 1 going in the back, 1, 1, 1, 1. So another way you can look at this is if you draw a line of symmetry, we would see that this is the same as this because they're both seeing the same things. If you go down, you see it's seeing the same thing. If you go down this way, it's seeing the same thing. And the symmetry is another way of helping you see that. Same thing with this hydrogen and this hydrogen. They see the same things. If you go up, same. If you go down, same. And if you go down, same. So these two are going to be the same. And now why isn't these two hydrogens part of that same pink signal? The reason for that is because these hydrogens here and here, they're fixed on this double bond. So they're not going to be able to rotate freely like this methyl. See, there's no double bond here. Methyls are able to rotate, so they're all going to be, all three of these, 1, 2, 3 hydrogens are the same, always on that methyl. So these hydrogens on the methyl can rotate about, and they're going to, see the molecule the same, from the same signal here and here. But over here, they're not going to see the same thing, because this double bond, you can't rotate on it. It's very rigid. So this pink signal is stuck seeing this CH3 group, whereas this is going to be a separate signal because this immediately sees this CH2 group right here, and it does not immediately see that CH3 in the same way that this pink signal does. That's why we're going to call these two their own separate signal. And again, the symmetry is a good way of helping us see why these two would be the same. And finally, this is it's on the line of symmetry, so it's going to be its own separate signal. It's going to be its own separate signal, and see the one that's the hydrogen that's sticking out at us versus the one that's going out in the back of the molecule, they're seeing the same things regardless. These are able to see the same things because they're not on a rigid double bond, and on top of that, we don't have any other wedges or dashes in the molecule that would influence what they see, and we'll see in other examples what I mean by that. A carbon has to be bonded to 4 things if it's neutrally charged. So we have 1, 2, 3, whereas the 4th bond has to be here in the back. We have the oxygen on the wedge. That must mean that we have to have a dashed hydrogen in the back. So we have a dashed hydrogen, same over here. And here we have CH2 group, one's sticking out, one's going in the back, one's on the top of the molecule, one's in the back, top of the molecule, in the back. So the first easy signal that we can identify is this hydrogen right here and this one right here. They're obviously the same because they're on the same thing. This one, they're directly attached to the O, same thing. This one and this one. So we're going to call that the same signal, the yellow signal. This hydrogen that's on the same carbon with the wedged O, this hydrogen that's on the same carbon as the wedged O, is going to be the same signal. And again, if you wanted to look at it in terms of a line of symmetry, you can draw one here, for example. And sometimes molecules have more than one, but I'm just drawing it this way just to show you an example. This and this is the same signal by symmetry, that hydrogen. Something to keep in mind now for this type of molecule is the wedges and dashes. So here we have an O on a wedge and a hydrogen on a dash. So that means O is going to be, if the molecule was flat on a table, the O would be sticking above the table and the hydrogen would be underneath the table. So this hydrogen that's sticking above the table is going to see the O above the table. Same with this hydrogen. Same with this hydrogen. Same with this hydrogen, the wedged ones. So we're going to have to be careful with this one and show that these hydrogens are the same, the blue signal, the ones that are dashed, but these hydrogens are not the same, the ones going out in the back, because they, unlike the wedged ones, these dashed ones are going to be experiencing the dashed hydrogen. They're not going to be seeing the OH. So I'm referring it to as what are they seeing, but if you want to be really technical, it's all about, having a different environment will give you a different chemical shift when you're looking at a spectrum. And we know that oxygen is very electronegative. It's going to be hogging those electrons, so it's going to de-shield anything that's like close to it. So the closer you are to that oxygen, the more de-shielded you're going to be. So because these ones are so close, to the oxygen, they're going to be more de-shielded than the green signal. So that's another way to look at it. So the first thing I'm going to look at is the two methyls. They're going to be the same because they're going to be the same signal because not only are they going to be hydrogens on the methyl, they're going to be seeing the same stuff. So these hydrogens are next to this hydrogen in the same way that these are next to this hydrogen, so on and so forth. They're seeing the same things. So that's one signal. And these hydrogens in the back are going to be the same signal as well. And again, we could draw that line of symmetry down the middle and see that they really do match up. They're seeing the same things. And what about these two hydrogens? So we have a hydrogen in the back and a hydrogen in the front. So what is this hydrogen in the back seeing? The hydrogen in the back is seeing two hydrogens in the back. But this hydrogen in the front, it's going to be seeing a methyl group. And a methyl is a whole lot different than just a hydrogen. So it's going to have a different chemical shift. Therefore, it's going to be a different environment, which means it's a different signal. So we have one signal here. Let's draw that a little smaller. So we have one signal here and one signal here. So we have 1, 2, 3, 4 signals. Alright, so for this compound, let's draw in the hydrogens. 1, 2, 3, 1, 2, 3, one facing up, one facing down, and that fourth bond hydrogen. So again, these are hydrogens on a methyl. They're going to be equivalent. These are hydrogens directly attached to a carbon that has a methyl attached. So this hydrogen is attached to a carbon, which is attached to a methyl group. This hydrogen is attached to a carbon, which is attached to a methyl group. And if you go this way, you see the same thing, and if you go that way, you see the same thing, and this way they see each other. So they're equivalent. But what about this signal right here? So we see a wedge up hydrogen, which sees a wedge up methyl, and a wedge up hydrogen. What about this wedge down hydrogen? It sees a wedge down methyl and a wedge down hydrogen. So this hydrogen sees one wedge up methyl and one wedge up hydrogen in the same way that this dashed hydrogen sees a dashed hydrogen and a dashed methyl. So they're seeing the same things. Therefore, it is the same signal. So what about this compound? 1, 2, 3, 1, 2, 3, drawing in our hydrogens. Hydrogen in the back for the fourth bond, hydrogen in the back. And we have a hydrogen sticking out, a hydrogen in the back, hydrogen sticking out, and one in the back. So again, methyl, they're going to be the same, attached to the same things, experiencing the same things, therefore they're the same signal, the hydrogens on the methyl. And we have a hydrogen in the back attached to a carbon that's attached to a methyl, same thing, same signal. But for these wedge up hydrogens, they see a wedge up methyl. And these wedge down hydrogens see a wedge down hydrogen. And again, carbons are different than hydrogens, so they're going to be seeing different things. So the wedge up sees the same thing, which is the wedge up CH3 groups. And there is a separate signal for the wedge down hydrogens because they see the wedge down hydrogens. Alright, so 1, 2, 3, 1, 2, 3. Hydrogen in the back, hydrogen in the front, hydrogen in the front, in the back, front and back. So again, hydrogens on a methyl are going to be the same. They're experiencing the same things. So we're going to call that same signal. And we have hydrogens again attached to a carbon attached to a methyl, so that's going to be the same signal for both of these hydrogens. And what about down here? We have wedge up hydrogens and wedge down hydrogens. So what does this wedge up hydrogen see? Next to it, it sees a wedge up carbon, and a little further down, it sees a wedge up hydrogen. So let's just call that its own signal for now. Let's call that blue. So this one is seeing carbon close, hydrogen far. This one is seeing hydrogen close, carbon far. They're basically flipped in what they're seeing. Again, the carbon and the hydrogen are different and are going to affect the chemical shift different. So that's why I'm going to give this, for now, its own signal. So the one dashed in the back has its own signal. This wedge up hydrogen has a wedge up hydrogen close and a carbon far in the same way that this one had it. So that's going to be a green signal. And this wedge down hydrogen sees the carbon close and the hydrogen far in the same way that this one did. So again, this one saw carbon close, hydrogen far. So this one saw carbon close, hydrogen far. So this is going to be the same signal as that other hydrogen. And notice how there's a green dash matching with a green wedge and a blue dash matching with a blue wedge. So every molecule is different. That's the moral of the story. You can't just memorize, oh, dash goes with dash. And no, it depends what they're seeing. The environment changes everything. So every single molecule is going to be different. And for this compound, we have 1, 2, 3 hydrogens, 1, 2, 3, and 1 here for that fourth bond for that carbon. 1, 1, 1, 1 sticking out here, and 1 in the back here. And then obviously this one and that one that's already written on the molecule. So something to keep in mind, why would these two methyls be considered the same? If this methyl is closer to, this versus this methyl is closer to this, and they're different. And the reason for that is because this carbon, see, like this is a rigid double bond, you can't rotate it. So what's stuck on one side will be stuck on one side, and what's stuck on the other will be another. But this carbon right here, this whole thing right here can rotate. It's going to rotate like that way or that way. And so this carbon will end up being able to see this, and this carbon will end up being able to see this side, even though you normally think it wouldn't, but it can because of that free rotation. We have these two methyls the same, this hydrogen being different because it's the only one sandwiched, in that particular type of spot. We have this hydrogen as its own signal, and this as another signal. Why is that? Because this sees this region, and this sees that region, and they are different. Again, this is yet another different hydrogen. Oh, and this hydrogen down here is different. This hydrogen is its own signal, and lastly, this these two hydrogens are the same signal, because regardless of whether it's on top or on the bottom of the molecule, wedge up or wedge down, or dashed, it's going to see the same things, so it'll be considered one. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 different signals. And what about this molecule? We have 1, 2, 3 hydrogens, one hydrogen here, one that's wedge up, one that's wedge down, one here for that fourth bond, another one here for that fourth bond, one hydrogen in the front, one in the back, one in the front, and one in the back. So starting on the left side, we can see that this hydrogen is its own unique signal. This methyl is going to be its own unique signal. This hydrogen is going to be its own unique signal. And this hydrogen is going to be its own unique signal. It's a little darker pink than the one up there. And why are these different and not the same? Is because this is a very rigid double bond. They're not going to rotate, so this is strictly going to see this, and this is strictly going to see that side. This is going to be its own unique signal. This is going to be unique. And why is this hydrogen on top going to be different from this hydrogen on the bottom? This is already an existing chiral center, because we have this group right here, which is very different than this group down here. So we have one unique group, 2, and then 3. They're all very different, and then obviously that fourth group would be the hydrogen. So since we already have a pre-existing chiral center, and we can make a fake chiral center here, so to speak, so we can do like the Q test, or let's say we replaced one of the hydrogens by like a halogen, chlorine for example. So let's say this was chlorine. We would have one unique group, 2, 3 for that hydrogen, and then that fourth group would be that imaginary chlorine. So like that's a test we could do. So we have a real chiral center and a fake chiral center, so to speak. So it would be distereotopic. And so because these two hydrogens are distereotopic, they're going to be different signals. This would be yet another different signal. This would be another different signal. This would be another different signal. None of them are the same so far. They're all different. So this would be another different signal. So in total, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different signals in this molecule. The reason why all of these are different, so we see that this sulfur sticking out is in the front, and there's a sulfur sticking out in the back. So the one in the front has its own front and back hydrogens, and the sulfur in the back has its own front and back hydrogens as well. So it's kind of thinking about it like, for example, if you had a drawing of a dog, you have a front leg, 2 front legs, and 2 back legs. So these both are front legs, these both are back legs, but we see that one of the front dog legs is sticking out more than the other front dog leg. So this would be, although they're both front, this one is more in front than this one. And although these are both in the back, this one is more in the back than this one. So we see on the left side and on the right side of the dog. Similarly, here we see a front and back, and here we see a front and back. But obviously, these ones are more in the front than these ones. These ones are more in the front because this entire sulfur is in the front. This entire sulfur is in the back, so these are more in the back. So this would be the most in front. This would be this, even though this is in the back, this is the second most in front. Then this is the third, and this is the fourth. So they're just different in that respect. That's like the best way I could explain it.